Welcome to everyone. Good morning. This is the seminar number 3 of the 2022 seminar series of the Magnetic Resonance Laboratory. In this opportunity, we have Liza Herrera Diez that she's going to present her work. And now we are waiting for Javier that he's connecting for the presentation. Yes. Okay, so Javier is going to present the Liza, and she can start with her presentation.
Okay, I'm sorry, I have a problem with my computer. Okay, hello Liza, hello everybody. It's a pleasure for me to introduce Liza Herrera Diez. For a quick overview of her CV, I can say that she has an interdisciplinary background in physics and chemistry from 2003 to 2007. She studied physical chemistry in the National University of Cordoba in Argentina from 2008 to 2010. She did her PhD at the Max-Planck Institute for solid-state research while enrolled in the physics doctoral school at Ecole Polytechnique Fédérale de Lausanne. During her PhD, she worked on magnetic domain wall dynamics and magneto-transport in devices based on diluted ferromagnetic semiconductors. She also designed and realized the concept of light control of magnetic properties by surface functionalization with organic dye molecules in such devices. From 2011 to 2012, Liza was working as a postdoctoral researcher at the Institute Néel in Grenoble. During his postdoctoral stage, she worked on electric field control of magnetic anisotropy and domain wall dynamics in ferromagnetic field effect transistor devices. Since 2013, she's a CNRS researcher at the Center for Nanoscience and Nanotechnologies in Paris-Saclay. And her main scientific interests are oriented towards the control of domain wall dynamics in multifunctional nano devices, mostly using magneto-ionics and interface engineering. And the talk she will present today is entitled Magneto-ionics, using ionic motion to control magnetism. Once again, it is a pleasure for me to hear about new results Liza will show us in her presentation. Liza, you can start when you want. Thank you very much.
Thank you so much. It is such a great pleasure to be here today. To know that it's that this is tested in my beloved Argentina. It is really a great pleasure for me to be given this presentation today. So let me see if I can share my screen properly. Just a second. Select the window, yes. Okay, let's go with entire screen. No. Allow, okay, but I'll probably just show my own screen now. I want to show this. Is this showing properly?
Yes.
Okay, now somehow I cannot move the slides. Just give me a second because I cannot.
Sure.
There are two things opening at the same time.
Maybe you need to share your screen instead of share your presentation.
Yes, so let's try again. Yes, select window. Oh, no. Yeah, I want to share. I can't share your screen. You must grant permission in order to share your screen.
Okay, I will give you permission.
Your entire screen. Yeah, somehow now I can, ahora no puedo hacer nada. Perdón.
Can you try now? I put you as an organizer. ¿Puedes ahora?
No. I say you must grant permission in order to share your screen. Voy a intentar salir y entrar de nuevo.
Okay.
¿Dudas?
Okay.
Okay. Bueno, vuelvo. Lo siento.
Ok, Lisa, ¿estás ahí?
Te escucho re malo. Ahí me escuché a mí.
Hola, Lisa, ¿estás ahí? Ahora sí te veo, pero estás muteada.
Lo intento de nuevo. Lo
Ok,
siento.
no hay problema.
Ahora me parece que sí va a funcionar.
Ok, esperemos.
Sí, ahora se puede, está visible.
Sí, ahora sí.
¿Me escuchan
Yes.
bien? Bueno. Bueno, lo siento.
It's okay.
Okay, I'm really sorry for the delays. I guess after 2 years of COVID, I thought I knew how to do this, but okay. Well, as I said before, it's a great pleasure to give this presentation today. So I will, as it was introduced before, so I will be talking about magneto-ionics, how to use ionic motion to control magnetism. So first of all, I will tell you a few words about where I come from. Okay. And laser pointer. Yes. Okay. So I am a scientist. I am a CNRS scientist at the Center for Nanoscience and Nanotechnologies. We are located in the southern outskirts of Paris. We have this nice building that you can see here. So it's relatively new, and we have different departments. I work in the nanoelectronics department, and so as I said, we moved here a few years ago, and it's a very nice area in this the campus of the University of Paris-Saclay. So we're close to colleagues, for example, from Thales and from Ecole Polytechnique. So it's a really nice place to be. So well, I want to start this presentation by giving you by basically telling you the motivation behind controlling magnetism with electric fields. So why do we want to control magnetism with a gate voltage? So so to tell you about that, then I would like to give you the context of the use of this. So then we know that there is a large part of the community in spintronics working in topics related to applications, and in particular to applications on magnetic memory architectures. So then a few of the most promising concepts out there right now are, for example, of course, the spin transfer torque memory concept, and there are all the things that are gaining momentum, like the SOT, the spin orbit torque based memories. Then you're probably also familiar with the racetrack memory, nowadays more also presented in the context of controlling the motion of skyrmions to store information. And then this is one of the important uses of the gating of magnetism in this VCMA type of architecture. So this stands for voltage controlled magnetic anisotropy. But before we go into this detail, so then what it's important to say is that what are the challenges? What do we want to solve with electric field control of magnetism? So, of course, I mean, one of the challenges for applications in spintronics are density. So we want to go smaller, and we want it to be very efficient in the very, very small scales. But one of the most important things, which is in the context also of one of the biggest challenges for society today, is the reduction of energy consumption in magnetic memories. So then, the challenges are to lower the writing currents that we need to write information while keeping long retention times. So so that means that we want to be able to write information on a state that has let's say a relatively low energy barrier, so then it wouldn't cost too much energy. But at the same time, you don't want this energy barrier to be too low so that it starts competing with thermal activation, because then your information is going to just die out. And we want to have this very strong and robust magnetic memory. So we need a compromise between those things. And of course, in other types of architectures, for example, in particular for SOT, so then we need, for example, field-free switching to improve charge spin conversion and to lower the resistivity in this prototypes. And in the racetrack memory design, then we want to control very well the domain wall or skyrmion pinning in nanotracks, and in particular for skyrmions also to be able to suppress the skyrmion Hall effect, which it's one of the problems, let's say, for a racetrack based on skyrmions. So where is electric field control of magnetism here? So one of the let's say the main selling point for applications is that it can provide us with a switch that can give us different states of magnetic anisotropy that could be used, for example, for toggling between a relatively soft magnetic state where we could write information at a relatively low energy cost, but without having to compromise for reliable information retention, because we could go from that state once we write the information we want with low writing current, then we could switch back to a relatively hard magnetic state where anisotropy is much higher. And then that state will keep the information for a very long time in a very reliable way. So then we wouldn't have to compromise anymore between these two things. So the E-field control will allow us to go from one to the other. And the same thing stands for the pinning and nucleation of domain walls and skyrmions in tracks. So we could control the pinning, the nucleation, and the annihilation of these magnetic structures. So this is really the selling point. This is why we want to use and optimize gating of magnetism for spintronics applications. So so now let me tell you how we can control magnetism with a gate voltage. So we have mainly two different concepts that are being investigated at the moment, or that have been laid out as possible concepts. So we have here on the left, charge effect. So what you do here, you have a device that looks like this. You have your magnetic film, an oxide, and a top electrode. So and then you apply a voltage between your magnetic film and your top electrode. And so you basically charge this capacitor, and you get charges at the surfaces of your two electrodes. One of them is your magnetic film. And so the trick here is that the magnetic film is a nanostructure. So then we know that the changes in charge accumulation at the interface can be very important for the magnetic properties. For example, we have materials with perpendicular magnetic anisotropy. We know that this perpendicular magnetic anisotropy is seated at the interface. It's an interface effect. So then if we can control the charge accumulation at the interface, then we have good chances of actually getting an effect on magnetism. And this is really what we do when we use charge effects. So the good thing about this is that it has high charging speeds because it's all electronics, and it is compatible with conventional electronics, and of course more compatible with any kind of application. However, on the downside, it is a volatile effect. So if you switch off your gate voltage, then the effect is gone. There's no more charge accumulation. And it is limited to the top interface. So then let's remember that we have a metal, and then this will be very, very much concentrated at the top interface. And then we know, for example, in the type of materials we want to work with, the substrate, the interface with the substrate is very important, because most of the time we have a heavy metal substrate, which gives us effects like DMI, and then it's important for spin orbit torque. So it is important to be able to access the bottom interface, which we cannot do with charge effects. Now, this is where ionic effects start becoming interesting. So the device designed can be seen pretty much in a similar way. So then we have a top electrode, a bottom electrode, which is a magnetic film, and some oxide in between. But here we will particularly go for an oxide that has a high ion mobility. So of course here, if we apply a voltage, we will still get charges accumulated at the surface of the two electrodes. But what we want here is that this electric field that we create will be enough to actually move ions in the oxide, not just polarize it electrically. And these ions can go up to the magnetic film, and the effects can be very big. And on the good side of this is that it is a non-volatile effect. Once the ions move, if you switch off the gate voltage, the ions will stay where they are. So that is a very important positive aspect about ionic effects. The effects are non-volatile. They can be very large, actually, as we will see later on. And they are not limited to the top interface. So they can actually go through the entire magnetic film, as I will show you later. We see that they can actually get to the substrate, which is an important aspect to control all the things other than the magnetic anisotropy. On the downside, well, it's ionic, so it's slow. So that is the difference with electronics, which is the charge effects. So the speeds are limited by the ionic diffusion dynamics. And as you will see later on, most of the ionic effects are based on reduction and oxidation of the magnetic ions. So then this could create problems with reversibility and cyclability. They could be affected by these chemical reactions that take place. So, so before I go into the ionic effects, let me give you an overview of what has been done with charge effects, because it's I will not talk about it today, but it's a very interesting side of electric field control of magnetism. So, for example, here we were able to show a few years ago that we could nicely go from out-of-plane anisotropy to in-plane anisotropy in cobalt iron boron MgO. And with this effect, we could show that if we kept a magnetic field applied constantly out of plane, we could actually toggle the magnetization from in and out of plane with only with the action of the electric field. And then other studies have shown, this is from collaborators at the Institute Néel in Grenoble, they could show that in platinum cobalt, they could actually write and erase skyrmions in the system just by the action of the electric field. And yeah, and all the groups have, well, again, the group in Grenoble, but also all the groups in Japan, they have shown that the DMI could also be affected by the electric field applied to the sample. So okay, here. So yeah, so then these are very nice perspectives, also from the side of the charge effects, even if these effects are volatile. So here, so this is really what I will be talking about today. So the magneto-ionics, which is ionic effects. So we can have different types of devices that could be used. So what you see on the top here are solid state devices. This is basically the concept I explained a little bit earlier. So we have an oxide that has a high ion mobility, and then the whole thing is a typical, like a field effect transistor. Everything is solid state, and we can fabricate it with the usual nanofabrication tools that we have in the clean room. And then there is ionic liquid gating, which is something that we like a lot in my group. We do this a lot. So here, what you have is that you have your magnetic film, and then you put this ionic liquid on top. So the ionic liquid is it's basically a molten salt. It's a liquid, but it doesn't have a solvent. It just has positive and negative ions. So then if you put it in a sandwich structure like this, and then you apply a voltage across, then you could get a huge polarization, because the ions would actually move towards the counter electrode, and you could get very large electric fields. And it's a very, very simple device geometry. So you just put the liquid on top of your film, and it just works. And it can be done over large areas, which allows you to get to measure, for example, XPS or XAS techniques where you would like to have a relatively large area where you can that you can measure. So it's very useful to understand the mechanisms. And then I will show you some of our work done with ionic liquid gating. And as I said earlier, so most of the things happening here are related to electrochemical reactions. So the metal turning into an oxide and back and forth through the action of a gate voltage. So then a lot of people are actually going full electrochemistry, and then are doing this in an electrochemical cell, where they can actually control all the ions and the potentials that they use. So this allows really for the in-depth characterization of the electrochemical reactions. So so then, what are the mobile ions that we talk about when we're talking about this ion mobility in the system? So a lot is being done with oxygen ions or oxygen species, let's say OH, which is not entirely clear. So oxygen species that can produce oxidation. So then this is one of the pioneering works done in 2015. So this is what I showed you before. So it's cobalt gadolinium oxide and a top gold electrode. So here, what they showed initially in this top line of hysteresis loops is that if you change the oxidation level at the cobalt interface, so let's say if you on purpose insert a metallic gadolinium layer in between, then you will get this series of different loops. So then they said, well, if we're actually oxidizing the system with a voltage, then we should be able to see these changes that we did on purpose, growing the system ourselves. We should be able to see the system going back and forth between all this with the action of a gate voltage. And this is really what they saw. They took this film and then they apply positive or negative voltages, and then they could really go through all this different state, and they could really show that they could propose really that there was a front of oxidation from the gadolinium oxide that would come down to the cobalt interface and back out, depending on the sign of the voltage applied. So so this is the oxidation. This is something we could show as well in one of our systems. So we use platinum cobalt. Here's in the ionic liquid geometry. And we could really see by XPS that the metallic peak of the cobalt would go into, would decrease in intensity, and then also give rise to another peak at higher binding energies, which is compatible with oxidation. So the cobalt is really getting oxidized. So this is something that is very important and is different from the charge accumulation effects. Here, the magnetic films are really being oxidized. There's a chemical change that happens when we do ionics. And this is another example from one of our most recent studies on tungsten, cobalt, iron, boron. Here we have cobalt and iron. And then we could also see by XPS that this is as grown, annealed. So we see that there's not much of a change in the oxidation level of the system after annealing. But then after electric field, there is an important change in the oxidation. We can clearly see how the oxidation of the iron and of the cobalt appear as a function of the electric field. And what is nice also is that the oxygen peak, the oxygen spectra also shows how the oxygen is being pumped into the system through electric fields. So here you see at the beginning, we have a peak that it's mostly due to this hafnium oxide that is there at the beginning, which we actually need to have because otherwise the cobalt will be completely oxidized in air. So we need to protect it. And we put hafnium oxide, so it's also an oxide that has high ion mobility. So then there is some oxide already in the layer, and it's here. But then when we switch on the electric field, then we see that there is this other oxygen peak here that grows a lot thanks to the electric field. So then we could really identify that this is a different kind of oxygen that is being pumped by the electric field. So then, so then we can see that the oxygen species can have a high mobility and they can really interact with the magnetic system. And I will talk about this later on, but then this is very much related also to the atmosphere. There's a lot of oxygen that is being pumped from the atmosphere, not only from this high mobility oxides, but also there is an interaction between the oxygen that is in the system and the water and oxygen from the atmosphere. So, but there is not just oxygen. So then other groups have shown that, for example, hydrogen ions or protons could be used for magneto-ionics. So then in this system, it's a very similar system as the previous one with gadolinium oxide and cobalt. And then they start here from a cobalt oxide state. And then what they propose here, which is very, very interesting, is that what I said before, that this really depends on how much water there is in the atmosphere. So they really propose that there is a hydrolysis of ambient water on top of the top electrode, and then after this, then the protons are being pumped into the system. So then they could nicely show this by showing here's the virgin sample. If they apply a gate voltage in ambient conditions, they get this perpendicular state. And then if they do it in vacuum, they don't get the effect. If they do it in dry oxygen, they don't get the effect, which is important to back up the story about this being hydrogen and not oxygen. But if they do it in a nitrogen atmosphere with some water inside, then it's okay. Then it's PMA again. So then they could really show that this is related to hydration, to the water, an exchange of oxygen of hydrogen with the water from the atmosphere. So this was really one of the studies that pointed this out quite clearly, that there was a need to have water in the system. And this is something that, for example, in our case, we have seen with the tungsten system that I showed you before. I will go into detail later on, but this is a system we had to anneal and before doing magneto-ionics. And then we could see that if we take it out of the oven and we try to do magneto-ionics, it doesn't work that well. So we have to leave it for some time in air. And then if we do magneto-ionics after that, then it will work. So then this is clearly an indication that the system is sort of hydrating again after letting out all this water and oxygen during the annealing, that it needs to get this back to actually have an efficient magneto-ionic response. And then it has been shown as well that nitrogen ions can be used for magneto-ionics. So this is an approach that is more on the electrochemistry side that I show you at the beginning. So here they actually they grow the magnetic film in situ, and they can with cobalt oxide, they can really oxidize it fully and then recover it fully, and then recover cobalt in the ferromagnetic state. So they can go back and forth very nicely from a complete metallic state to complete oxidation. And this is what they can do as well with cobalt nitride, which is here. They can get also a very nice response between the fully the metallic cobalt and the full cobalt nitride. And what they extract from this, which is it's very interesting because they can show that with nitrogen ions, the process seems to be more ordered, more homogeneous. They get a more ordered front of nitration inside the layer, which could be important to reduce defects in the system, for example. And also they could show that the energy barriers to move nitrogen are not as high as in the case of oxygen, which could be an outlook towards even lower energy and lower voltage operation for these devices. So, well, but this is not limited to ferromagnets. So people have been investigating magneto-ionics in other types of magnetic systems. So what is really interesting is what has been done with synthetic anti-ferromagnets. So actually, from this same group, before they did this work on magneto-ionics, they could actually show that domain wall velocities could increase a lot if the magnetic moment of the domain wall could be compensated. So then what they did is to build a stock like this one, so that is anti-ferromagnetically coupled. So then they have a top layer where they were observing the domain wall motion, and then a ruthenium layer which couples it anti-ferromagnetically with a bottom layer. So then there will be a mirror of the magnetic moment of the domain walls that are on top. So then they could obtain this ginormous domain wall velocities. So then they took that concept and then they said, well, I mean, if we have two layers that are not fully compensated, we can play actually with the top layer. So then here they used an ionic liquid. They just place it on top of this stack. And what they did is to actually oxidize the top layer. So then that would bring it closer or further away from compensation with the bottom layer. And then when they get close to compensation, then domain wall velocity shoots up. And that's really what they show here. So then they go from a very high domain wall velocity to a much, much lower state. So then this is a variation of hundreds of meters per second. So this is a very nice way to show that this can go beyond the changes that we can do with anisotropy. I mean, this is really something that it starts being really relevant for applications. So, so this was a really neat way of controlling domain wall velocity, not just changing anisotropy as we would usually do or has been done a lot in the literature. And this, of course, can be done as well in natural ferromagnets. So then here they showed that they could control well, here, I mean, it's gadolinium cobalt. So here there's really two sublattices that are aligned against each other. And then there is a dominant magnetic moment either from the gadolinium or the cobalt. And then the electric field could allow to go from one to cobalt dominated to from cobalt dominated to gadolinium dominated. And here they measure the typical signature of a ferromagnetic system, which is the compensation temperature. So when you measure the coercive field of the systems as a function of the temperature, then there's a divergence of the coercive field at the compensation point. And then, as I explained before here, the compensation point can be moved around with a gate. So then if they would record this as a function of the gate voltage, they could really see that this compensation temperature could be moved around with the gate. So, yeah, so then I wanted to give you this overview before showing you a little bit more about our results, which is what I'm going to do right now. I hope we gave you kind of quick span of what's being done, different ions, different magnetic systems. There's really a lot of activity right now in magneto-ionics, and new things come out every day. So it's very, very exciting to be working on this field. So so now, yeah, as I said, I want to show you a little bit more of what we have been doing. So let me show you this first system. So this I showed a little bit before. So it's platinum cobalt. So we put this hafnium oxide layer to protect it from oxidation, and also because it's a very it's a system. It's an oxide that is used because of its ion mobility. So it's actually used a lot in memristors, for example. So it's an oxide that is really adapted for ionics. So so we put it on top. We put the ionic liquid on top of that. So what we do here is that we apply a voltage for a given amount of time, and then we look at the magnetic state because, as I said earlier, it's non-volatile. So here you can see very well, we go from an in-plane state to a very nice perpendicular state where we can see magnetic domains. So with 1 minute of applying this this gate voltage. So well, I already said a few things about oxidation. But then at the time when we saw this, then we went straight to the literature to find out what this could be related to. And we found this very nice study, which is a reference for PMA materials, where they could control the oxidation of the cobalt oxide interface. And they could see that as a function of the oxidation time, they would see the system going from in-plane from in-plane magnetized to perpendicular anisotropy back to in-plane magnetized. So then if there's too little oxygen, it's in-plane anisotropy. If there's too much oxygen, it's in-plane anisotropy. But then there's a window of oxidation where the system favors perpendicular anisotropy. And this is what we linked to our system. We said, well, it's a system that comes out of the deposition chamber. It doesn't is under oxidized. We pump some oxygen inside because we apply a negative voltage, which was compatible with oxygen species moving towards the magnetic film, and then we recover PMA. So this this is really a gate-driven oxidation that promotes the transition between the in-plane and the perpendicular anisotropy. So, so here, this you have seen already. So we turn to our collaborators to get a little bit more characterization about the chemical characteristics of our magnetic film. So we could nicely see by X-ray photoelectron spectroscopy with our collaborators in Italy that there was indeed a signature of oxidation of cobalt. It was the same what we observed from XAS done by our collaborators in NIST. And what was interesting at this point is to look at the platinum. Then we could see that there was a shift in the peaks of the platinum. So then we couldn't see an oxidation of the platinum, but we could see that there was some kind of change in the chemical environment of the platinum. So then at that point, we started thinking that ion migration might not just reach the cobalt hafnium oxide interface, but it might also go further than that, which was one of the motivations of using magneto-ionics, going deeper than just the top interface. So then we thought immediately to look at DMI. So I think this audience is very well aware of DMI, but I would just say very fast that so that the DMI is an antisymmetric exchange interaction. So which is different from, for example, the Heisenberg exchange interaction, where you have all your spins aligned in one direction. So then here the DMI is actually an interaction that would rather have the spins aligned perpendicular. So then this generates favors non-collinear structures. So then it's a magnetic order, but it's non-collinear. So it can be, for example, helical structures, skyrmions, and for example, it favors the appearance of Néel magnetic domain wells in perpendicular materials, which would normally have Bloch magnetic domain wells. And then one way to evaluate the and to get the values of the DMI is Brilliant light scattering. So one other important thing about DMI is that it's chiral. It imposes a chirality on the system. That means that the spins winding in one, let's say a clockwise direction is not the same as winding in the anti-clockwise direction. So this will be given by the sign of the DMI. So then this can be probed if the propagation of spin waves are measured. So then a spin wave propagating in one direction with the spins winding, let's say in the clockwise direction, will not be the same as propagating in the opposite direction. This is really what you measure. I mean, there will be a shift in the frequency of these spin waves, and this is related to the DMI. So this is what we measure with the Brilliant light scattering. And then this allows us to get the parameter and the sign of the DMI. So, so this we did with our colleagues in Paris, who are the experts on BLS, and we could obtain the values of D, and we could see that it has a negative sign, but it's in absolute value is decreasing as a function of the gating time. So we thought about this, and then we know that the ions can go very far. This is the proof that there is something going on, because in these systems, the DMI mostly comes from the interface with the bottom heavy metal ion atoms. So then our interpretation is that these ions are probably decoupling the platinum and the cobalt layers due to ion intercalation. And then this we could see very well, because we know that this is domain wave velocity as a function of the perpendicular field. We could see that this affects greatly the maximum domain wave velocity. And then we know that the domain velocity here depends on the DMI. So this made a lot of sense with respect to this measurement. So it seems that it might be due to this ion intercalation. However, we cannot forget that, for example, in charge-based devices, there still is a change in the DMI that is induced by only playing with the top interface. So then we know that the DMI comes from the asymmetry between the two interfaces. So then, I mean, we know very well that we are also changing very much the top interface. So this will definitely contribute to the final result and to the complexity of the system. But we do have evidence that there is a change also in the bottom interface. So, so this here is a similar study. So here we have tungsten, cobalt, iron, boron, aluminum oxide, ionic liquid. And here we see a similar effect, the DMI reducing in absolute value as a function of the gating time. What is different from this system is that we had to anneal it to obtain PMA. So in this system, it's not enough just to pump oxygen to get PMA. So then we have to start from an annealed state, which is this black curve, and then we can bring it back to the in-plane anisotropy as we did with all the systems, as you can see before, but after, sorry. This is the system what I showed you before, the XPS. We can see the oxidation of the iron, of the cobalt, and the appearance of the growth of a peak of oxygen after voltage application. So this is here what I was trying to explain before. In the as-grown state, so before with the cobalt, I show you an as-grown state that was exposed to negative voltages, and then we just got PMA. So here, there's no PMA, no DMI, no gating effect at all. But it is known for cobalt, iron, boron, tungsten, and especially without an interface with MgO, that the PMA has a large contribution from the structure of the cobalt, iron, boron, tungsten interface. So then here in the amorphous state, there is really not this contribution from the cobalt, iron, boron, tungsten interface to promote PMA. So then no matter how much oxygen we pump into the system, there is really not much happening. So then we really have to anneal to really get a nice interface, nice crystallized interface between the cobalt, iron, boron, and the tungsten to actually promote PMA. And then once it's there, then we can pump oxygen and see changes in the PMA. But it's there's a main difference with respect to the previous study. So here we get DMI, which is the DMI plot that I showed you before, but it's not reversible. So you cannot go back from this pink state to the black state. And this makes sense if you think about what we're doing. So we're crystallizing the system. So it's highly likely that the ionic diffusion in the as-grown state is in an amorphous state is easier than in a crystallized state, where you probably have to migrate ions only through the grain boundaries and not everywhere like you would do in an as-grown state. So so then we said, well, maybe we can find a compromise. Let's anneal, but at a lower temperature. And this is what we did here. It is partially reversible, so then it goes in the right direction because it's probably just partially crystallized, but we get almost negligible DMI. So then what we learned from this is that if the system needs to be annealed, then we're probably going to lose in terms of magneto-ionic efficiency. So I think that's an important message for, especially for these tungsten systems where we need this annealing to get this very nice magnetic properties like strong DMI and strong PMA. And then the last study that I want to show you, I'm not sure if I'm taking too much time. I didn't check when we started, but do let me know if I'm taking too much time. So so then this is once again a similar system, cobalt-iron boron, but this time on tantalum. Once again, hafnium oxide ionic liquid. So, and the top electrode. So here we start, like in the cobalt case, so it's a state that doesn't have PMA. So if we keep adding, we apply a negative voltage, we pump oxygen into the cobalt-iron boron or towards the cobalt-iron boron, and then we see that the system starts going to PMA. Then we have, at some point, for a given gate voltage and gating time, we have a nice PMA state. But if we keep oxidizing, then the PMA will decrease. So then this really resembles at the study I showed you at the beginning. If it's too little oxygen, it's in plane. If it's too much, it's in plane. There's a small window where you can get PMA. This is really what we see here, and we see the full range with the gate voltage. Now, what is interesting is that, so we seem to have already from this, so then this is the remanence as a function of the gating time. So then you can see the remanence going up from this state to this state. There's the first ramp up, and then it ramps back down. So when it goes in this direction. Then you can see that it shoots up quite a bit, and then the second line is a lot. It has another slope. So then we could probably tell from this that the processes are not the same. This to this is not the same as this to something else. So this is really what we wanted to probe here, and so then we called the under oxidation to PMA regime 1. And then PMA to in plane, but because of over oxidation, regime 2. And what we can see is that in regime 1, we could only go one direction. We could go from this state to a perpendicular state, but we couldn't go back with the voltages we can apply. This doesn't mean that it's impossible, but with the voltages we can apply, we couldn't go back to the initial state. So this is what we're showing here. It goes this way, but it doesn't go back. However, the second state, PMA to over-oxidation, which goes back into the plane, this was perfectly reversible. And here, for example, we could cycle it many, many times, and it was going back and forth very nicely. So then once again, we understand more and more that these two regimes are really not quite the same. So this is really our interpretation of what is going on. So then if we start from a system that doesn't have, hardly has any oxygen at the interface between the cobalt-iron boron and the oxide, then it is likely that we have binding sites for oxygen that are non-equivalent. that we have some binding sites that are extremely favorable and low energy and decrease the energy of the system. And then that oxygen would probably bind preferentially in those states because there's no oxygen anywhere. So then there will be a first wave of oxygen that would bind into this more favorable states, favorable sites, sorry. And then that if we keep adding oxygen, then the oxygen would just go somewhere else in interstitial sites or maybe more into the layer. And what is interesting is that, and then this is the part that can go back and forth. So the part where we have oxygen that might be less bound to the layer. So why am I saying this? Because we start from metallic. I mean, we're going to simplify a little bit the system because we have cobalt iron, but this is an iron-rich film. So then we could simplify it to the point of saying that we just have iron. We could do the same with cobalt. But here we start, let's say, with metallic iron before we do anything. And then if we start adding oxygen, we're going to oxidize this iron. So it's going to go from iron, metallic iron to iron 2+. So that is a proper electrochemical reaction. It's a proper exchange of electrons in the system. So this probably has a relatively large energy barrier to go forward and back. However, if we keep adding oxygen, so we might have a regime where we have iron 2+ surrounded by more oxygen species, but not quite yet in an iron 3 state. And this is something that that we can relate to, for example, the oxygen sticking probability of oxygen on iron that has been shown a very long time ago. So it has this this profile. So then, when there is no oxygen in the system, there is a fast decay of the sticking probability as oxygen is added to the layer, which could be related to an iron 2 type of electrochemical reaction, if we want to call it that way. So after that, there is kind of a flat line where we add more oxygen, but it doesn't really affect how much the sticking probability of that oxygen. So then this is really the part that we think is reversible. So then we think that there's no change in oxidation number from iron 2 to iron 2. Here it's just the surroundings of the iron 2 have more oxygen, but not necessarily the iron. So then this probably has a much lower energy barrier to actually go back here. And this is really what we see. This part seems to be a lot more reversible, or reversible at a, let's say, with lower energy barriers with respect to this. However, this is, I didn't show it, but if we overdo this part, if we overdo the oxidation, then we do end up on something that we cannot come back from. And then this is more probably related to this part. And also they say that they end up with iron 3 at the end of the process. So this is something that I didn't show, but we also know that at some point it's just too oxidized and it never comes back. So, well, so this is really what I wanted to show you today. I want to show you an overview of what's being done, an overview of what our results. I hope I could show you that with magneto-ionics, we can generate large changes in perpendicular magnetic anisotropy and DMI. That also it seems to be that it's much more efficient in amorphous materials with respect to crystalline materials or polycrystalline materials. And then also that reversibility and cyclability can be very much affected by the chemical reactions that are happening due to the ions moving around in the system. So in a more larger overview, I hope I could show you that magneto-ionics have great potential for spintronics applications and for energy efficiency, but also for all the types of new functionalities. For example, with what I showed you before, we could think about multi-level memories, for example, and neuromorphic applications. So there's really a whole field of perspectives where magneto-ionics can be used. And one important point is that for magneto-ionics, one has to make peace with the fact that magneto-ionics means chemistry. There is chemistry, there are electrochemical reactions, even if we're working with a device that looks like a normal device and there's no fluids of any kind around it. There is chemistry happening, and we have to think about the chemical reactions that happen inside to actually understand what's going on and how that impacts the effects on magnetism that we see. So interdisciplinarity is a must. It's a must to work on magneto-ionics. So we really want to talk more and more to people, for example, from, of course, from chemistry, but also from batteries, for example, that they know a lot about ionic motion. So it's really very exciting to connect with this other communities, and it's really bringing a lot of new insight to what we can do with magnetism. So this is my last slide. So then I want to thank all my collaborators for their support, in particular in our group. So the PhDs and postdocs working on magneto-ionics. So Rohit Pasha in particular, so he's the one who has done most of the work that I presented today. Tambi and Mariam, and of course my collaborators, Daphne Ravelosona and Damian Kailos, and collaborators all around the world for their theoretical and experimental support, and the funding, of course, from the European Union and French and local funding as well from Saclay. So thank you very much for your attention.
Lisa, thank you very much for this really interesting talk. I really like the result you present. I would like to open the session to questions, and we can start with the people from that is in the Meet platform, and then if someone in the meeting room has a question, I will kindly ask if they can approach to the Javier Curiales computer. So yeah, any question? I have a few questions actually. Okay, Javier has a first question, so go ahead, Javier.
No te escuchamos.
Sí. Okay, he's coming to ask this question.
Hello again. I have some problems here. My question is, Lisa, when you showed the velocity as a function of the magnetic field, and you showed that changing the gate voltage, you change the velocity. Is that velocity in the flow regime? And my question is about, are you changing the mobility, or just it's a shift in the curve?
That's a very good question, and there is a lot of debate. I mean, there's a lot of new work actually from the side of the just looking at the domain wall dynamics. So then there is really a plateau. There's not a slope there. So that's a typical thing that we see with cobalt iron boron. So then we go out of the depinning, and then you don't go into a linear flow regime as you will get from a 1D model. You sort of get stuck after the Walker breakdown. And actually in cobalt iron boron, if you would calculate the Walker breakdown, it would probably be around in the creep regime, like buried in there. So then what people have shown is that this plateau could be traced back to a value that depends on D over MS. So then this is what we wanted to show, that our D was changing a lot. And then, but then, of course, I mean, I didn't go into detail, but of course, you have to take into account MS as well. So it's D over MS, and then this can move this plateau up and down by quite a lot. Yeah. So then this is where we see the effects of the electric field. We say, well, if we change D drastically, then we should see a change in this plateau, and this is what we could show. So then it is beyond the depinning regime.
Okay, thank you very much. There is another question of Cynthia. Please go ahead. You can unmute yourself.
Okay, can you hear me now?
Yes.
Yes.
Okay, good morning, good afternoon, everyone. Thank you, Lisa, for the nice talk. And I have a question regarding, well, I have many questions here, but I am very interested in the interface between hafnia and cobalt. So in the first part of your talk, you were speaking about a stack with this ITO, I think, Ionic Liquid, and then hafnia and cobalt. And you said you were showing XPS, and you were saying that by this shift in the energy binding, you were saying, okay, this is in principle compatible with an oxidation of the cobalt. My question is, wouldn't we expect that cobalt oxide is anti-ferromagnetic, or because in principle the nature is still ferromagnetic, right? The nature of the samples.
Yes. Yeah.
Okay. So you don't observe a change in this regard. It's an oxidation, and you think this oxidation affects just the PMA somehow, right? So it's modifying a certain term, doing that the in plane is becoming PMA, right? Am I
Yes.
correct?
Yes, actually, I mean, I have to say that we haven't investigated a lot the fully oxidized state. So then, for example, if we take the cobalt layer, so it was a layer of 0.6 nanometers, so it was very, and then we could see the signature of the cobalt oxide from the XPS, but that tends to be, I mean, that was a little bit the debate as well, because if you have a very thin film, I mean, XPS comes mostly from the surface. So, but then at the same time, if you have a very thin film, I mean, what is the bulk? So, but then, I mean, we did measure in this system, we went to low temperatures to see the signature of the antiferromagnetic cobalt oxide, because it's antiferromagnetic at low temperatures. So then you wouldn't see it at room temperature. You wouldn't see an exchange bias at room temperature. But we couldn't see it. So then it means that it's not horribly oxidized. So then it's probably just what is enough to oxidize, to get PMA at the, to get PMA, to get enough oxygen at the interface to get PMA, but not fully oxidized. I mean, there are other studies, like for example, the one that I showed where they were looking at the nitrogen. There, they really oxidize entirely the layer, and they really go all the way, they oxidize back to 100% metallic. So that's really not our case. So we still have a magnetic state that is not perpendicular. So we don't fully oxidize, if that was the question. And yeah, the antiferromagnetic phase was not, we couldn't see it. So it shouldn't be that much of cobalt oxide.
Okay, thank you very much. Okay. Can I do a second one? Only a second one, please. When you were showing that not only by gauge but also by annealing, you were having some evolution. Have you considered or have you measured, for instance, polarization as a function of the electric field to see whether you have a ferroelectric hafnia?
Yeah, this is a very good question. So I discussed a few times with people from hafnium oxide, and because I was actually interested, before discovering this whole magneto-ionics thing, I really want to use hafnium oxide as a ferroelectric. And I realized that it's not that easy, because you have to have one specific phase of the hafnium oxide for it to be ferroelectric. So it's not, I mean, in our case, we just grow this system in an amorphous state, so it's just sputtering. So it's unlikely that we would be able to control so well the hafnium oxide phase. So then, yeah, I really don't think, we haven't looked that into detail, but I wouldn't, I would be surprised if we have a ferroelectric phase, because it's not too easy to get, actually. Yeah.
Thank you very much.
Thank you, Cynthia. I have a question. During the fabrication of, or in the fabrication of MTJs, in magnetic tunnel junction, you have something similar like MgO, covalent boron, and tantalum structure, or MgO, covalent boron, and tungsten. And when you anneal this structure, there is a boron migration toward the interface of the oxide. Do you think something similar is happening in your results as a function of the annealing temperature?
Well, I mean, in this case, yeah, it's tungsten, so it's not tantalum. But yeah, I mean, we expect that to happen because that's really one of the key points for the crystallization, that the boron would migrate out of the system. But we haven't really looked at the role of the boron, I have to say, in the magneto-ionics at all. I mean, I think it does not really contribute. I mean, it will certainly, I mean, it's a regular annealing process. Then in vacuum, 390 or any other temperature, and I would just expect the same result. So we do magneto-ionics after that. So then if the boron has migrated, we don't really expect that it would contribute at all. But yeah, to your question, yes, I mean, the annealing it's a standard annealing for this type of PMA material.
In vacuum, is annealing in vacuum. Yeah.
It's the standard annealing that we do for any other PMA material. Yeah.
Okay. I have another question. Why in some structures do you use ITO as an top electrode, and in other structures you use gold? Is there any reason for that?
Actually, we so the other devices that I showed with the gold were from the literature. Actually, in our lab we use exclusively ITO, simply because of the reason that it's transparent. So it's relatively conductive and relatively transparent. So then we want to be able to do microscopy through the gate. So we want something transparent so that we can look at the domain walls under the gate. So that's the only reason. We are starting to wonder now if there isn't a contribution from the oxygen of the ITO. So this is, we're asking ourselves the question because we see that sometimes, I mean, if we go too hard with the electric field or for a very long time, sometimes you can see the ITO just changes color if you look at the electric end of the process. And then we're starting to look into that, if the ITO is actually doing something and it's not just there to be an electrode. So yeah, it's a very interesting question.
Yeah. If I have another one, I really like the result in which you show that you can tune the moment compensation in SAF or in ferromagnet.
Oh, that's not ours. That's from a store parking in yeah. So that's not stuff.
But you also show in ferromagnets.
Oh, but that's not ours. I mean,
that's not ours.
Was
okay.
From the literature. Yeah, I would love to say that was ours, but it's not.
Okay.
The SAFs are from the Stuart Parking's group, because I mean he was also the one showing that this compensation could give you very large domain wave velocities, and then the other study with gadolinium cobalt was from MIT. So.
Okay. No, my question was in the sense that in ferrimagnets there is interesting effect, magneto-optical effect you can control via the tuning of the compensation. For example, thermal demagnetization or optical switching in an ultra-fast regime. Maybe if it could be interesting to explore this in the structure, you show, of the device that you show. But yeah.
Absolutely. I mean, this is really something where we're trying to nail down. We have all kinds of weird things happening. So we have a collaboration with Eindhoven University, with the Cook group, and we're into that. I mean, things are very complicated, but something happens, but we don't know what it is. But yeah, I mean, it is, as you say, a very interesting aspect, and we're looking into that. We think that something should happen. Yeah.
Yes. Okay, this is all from my side. I don't know if there any other question. There is one more question from Cynthia. Please go ahead.
It's me again. Have you performed impedance measurements to see if you can say, okay, I have mainly only one ionic mechanism or more than one?
No, we haven't done that. It is a very interesting question because, for example, I showed at some point that some people claim that there's oxygen transport, and for other types of measurements, they say, no, it's hydrogen. So then, there's a thin line because sometimes, it's the same oxide. So then, it could well be that there are other things happening in parallel, but yeah, we haven't looked into that, but it's it's definitely a very, very interesting and relevant question. Yeah, I can't give you the answer, but yeah, we should be thinking about more than one mechanism, and it shouldn't.
Yeah, mainly if we're interested in the application, I think they are going to ask you, okay, which are the mobile species here?
Yes, that's really what's the deal. To really try to understand what's going on, because it's all, especially when there's chemical reactions happening. That you make sure that you can really control it, and that, for example, reversibility and all these kind of things. That you really control it, and the only way of controlling that is really knowing what's going on. So then, this is really one of the important things to know. If there's just one species moving around, or there's many species moving in different directions because they have different charges, or this is still very much an open question.
Thank you.
Thank you, Cynthia. And if there is no more question, I would like to thank Liza again for your beautiful talk. I really enjoyed a lot.
Bueno, ahora en castellano, muchísimas gracias a todos, realmente muchísimas gracias por esta invitación, es un placer poder haber dado esta charla hoy, así que...
Muchas gracias, muy linda.
Muchas gracias, Liza, y entonces doy por concluido este tercer seminario de la serie de seminarios del Laboratorio de Resonancias Magnéticas, y la próxima semana nos va a dar una charla Rocío Ranchal desde la Universidad Complutense de Madrid. Con todos, muchas gracias y nos vemos la otra semana. Gracias, Liza.
Hasta luego, muchas
gracias. Los presentes.
Gracias, Liza.
Gracias, muy bueno.
Gracias.